Hello everyone again. Now we are going to look at the inductors in AC circuits, and we will generally use reasoning in learning inductors. For today's lesson, the objective is you are going to be able to describe the process occurring in AC circuits containing inductors. What is an inductor? An inductor is typically consists of an insulated wire wound into a coil around a core. So this is a picture of an inductor, and this is the symbol for the inductor. So what does an inductor do? An inductor is a device that stores energy in a magnetic field when electric current flows through it. So what is the difference between the inductor and capacitor? We know that the capacitors stores energy. I mean, both are storing energy. Both inductors and capacitors are storing energy, but a capacitor stores energy in a form of electric field, while an inductor stores energy in form of a magnetic field. So how does it behave when an inductor is connected to an alternating current source? As always, the source is alternating. This is the voltage change of the source with the time. It's a cosine function. And when it is connected to the inductor, the source is connected to the inductor, the current is going to oscillate in the circuit back and forth. And there is going to be a voltage drop across the inductor, and it's also going to change. The change of the voltage across the inductor is completely depend on the change of the current in the inductor. So voltage here is going to be equal to L times di over dt. This means that the change of the current with the time multiplied with the inductance of the inductor, and this inductance is a constant of the inductor, and it is completely depend on the shape of the physical shape of the inductor. Now, the voltage of the source is changing, and it is parallel to the inductor in this figure. So this is a cosine function, and the voltage drop across the inductor is also going to be a cosine function. So here, as you see, we have two formulas for the voltage across the inductor. Now, problem is, are the conductor and voltage in phase in this case? I mean, do they become maximum, minimum, zero at the same time or not? Let's first mathematically prove if they are in phase or not. Then I will explain physically the relation between them. Now we have two formulas for the voltage drop across the inductor. So let's equate these two, and we will write L di over dt equals, so VL cosine WT. From here, these two are equal to each other from previous slide. From here, we can write for di, the change of the current is going to be equal to VL over L cosine cosine WT dt. I'm going to integrate both this one and this one. So integration of di will be equal to integration of VL over L cosine WT dt. So from here, if we integrate all the currents, we are going to get IL, the current in the inductor, will be equal to the integration of this function. The VL over L is a constant, and the cosine of the integral of the cosine WT is sine WT. Actually, let me write first one W here, and then sine WT. So we got an expression for the current in the inductor. This is a sine function, but remember, for the voltage it was a cosine function. So let's make both cosine. We know that sine WT from trigonometry, it is equal to cosine WT minus pi over 2. So now let's insert this one. The current change, the expression for the current change will be VL over WL cosine WT minus pi over 2. Now we have two functions, one for the current in the inductor and the voltage VL of the inductor from our previous slide. Remember, it is equal to VL is equal to V max cosine WT. Sometimes this is shown with big VL. So these two functions are cosine function, but as you see, mathematically it is seen that the current lags pi over 2 degrees behind the voltage. So there is a phase difference between them. And in this case, the voltage is 1/4 period ahead of the current, or the current lags behind the voltage. Now let's go back and see physically what happens here. Now this is the current change, and this is the source, and the voltage of the source and the current of the source are both changing with the time. The voltage drop here, as you see, depends on the rate of change of the current. When the rate of change of the current, di/dt, is big, it means voltage is big. Now please look at the rise of the voltage from 0 to a maximum value. So the rate of change of current is big at the here, or it is bigger here. So to determine the rate of change, we look at the slope. The slope here will be bigger than the slope here. So it means that at the beginning, when the current is starting to increase from 0, the current is 0, but its rate of change is very high, which produces a high voltage here. So when the current is 0, approximately starts to increase, the voltage is a maximum value. This is because of the dependence of the voltage on the rate of change of the current. So physically, as we see that the initial current, when the initial current through the wire to the inductor is small, but rate of change of the current initially is very high, it produces a big voltage. So when the voltage is maximum, the current is 0, the voltage is ahead of the current. In this case, there is a phase difference between them. So we will represent their functions, their graphs like this. This is the current and this is the voltage. Here is their graphs. As you see from here, for example, let's look at here. So when the voltage is rising from 0 to a maximum value, it is maximum value, and as you see, the current is becoming it's from the negative value to a 0 value. Or let's look at here, as the voltage is at a maximum value, it decreases to a 0 value. Now the current starts to increase to a maximum value. As you see, there is a phase difference between them, which is 1/4 of a quarter. Why? Because this is t over 2, and this is t over 4. First, this is maximum. After t over 4 time, the current becomes maximum. So we say that the current peaks 1/4 of a period after the voltage peaks. So is there a resistance of the inductor? Yes, there is, and we call it inductive reactance. And when the current is flowing to the circuit, when it is going back and forth, some energy is stored in the wires in this coil, and the change of the magnetic field here produces an induced current. The current from the source and the current produced by the coil, they sometimes opposite each other, they sometimes are in the same direction. So there is a reactance against the flow of the current in the circuit, and we call it inductive reactance. And it is completely depend on the inductance of the inductor, which is depend on the shape of the number of the turns and other physical properties of the coil. And also it depends on the angular frequency. XL, which is the inductive reactance, is equal to WL. We can also express it as 2 pi FL. And Ohm's law is again valid here. Current is equal to VL over XL. So as you see, there's a direct relationship between the angular frequency and inductive reactance. When the angular frequency increases, so the reactance of the inductor also increases linearly. Okay, that's enough. Let's go to some problems and make some practice. Calculate the reactance of a 20 millihenry inductor at 60 Hz, 600 Hz, and 6000 Hz. From this graph, we will expect as the W increases, as the angular frequency increases, the XL inductive reactance will increase. Let's see if it is increasing or not. We know that XL is equal to 2 pi FL, and from here we can write that 2 pi 60 times 20 times 10 to the negative 3, and this is going to be equal to 2.4 ohms. And in B, again XL is going to be equal to 2 pi FL. It will be 2 pi and 600 Hertz times L is 20 times 10 to the negative 3, and making calculations will yield 24 pi resistance. The unit is here ohm. C, XL will be equal to 2 pi 6020 times 10 to the negative 3, and it will be 240 pi ohms. As you see, as the frequency increases from 600 to 6000, the inductive reactance increases from 2.4 pi to 240 pi. Next question is, what is the self-inductance of a coil whose reactance is 5 ohm at 60 hertz? We know that XL is equal to 2 pi FL, and from here we know XL, it is given 5 ohms. 5 is equal to 2 pi, F is 60 hertz times L, and L will be equal to 5 divided by 2 pi times 60, and calculations will give us approximately, in terms of millihenries, it will be 13 millihenry. So the next question, and this is the last question, a 50 millihenry inductor is connected to an EMF given by, this is the change of voltage of the source, and what is the reactance of the inductor? The reactance of the inductor is XL is going to be equal to WL. Now we know L, it is 50 millihenry, but we don't know angular frequency. But from this function, as you see here, 120 pi is the angular frequency, is equal to 120 pi. So XL will be equal to 120 pi times 50 times 10 to the negative 3, since it is millihenry. This is 50. Okay, calculations will give us 6 pi ohm. This is the reactance of the inductor. B, write an expression for the current through the inductor. Now, the expression, we know that IL is equal to I max times cosine WT minus pi over 2. To write the expression, first we need to find I max, maximum current. It is equal to V max over XL. So V max from this formula, it is 180 volts divided by 6 pi. It will be equal to 9.6 amperes approximately. So now we can write every term. It will be 9.6 I max cosine W. Instead of W, we know that it is equal to 100. It is cosine 120 pi T minus pi over 2. Okay, this is the expression for the current. So thank you for listening. This is the end of the lesson for the inductors. See you next time.